You are ready. I am ready, and I am pumped. Oh man, I am so pumped. I'm going to pump. Wait a minute. Hang on. We'll start that again. We are going to pump you up. Yes, we are. This is the big kahuna of equilibrium for today. I know we've gone through a lot of problems. You're going, huh? This is the big kahuna of all equilibrium problems. Not the problem per se, but how we're going to solve it. If you take your sheet, I'm trying to find it, got a mess here, and you look right here, and it says calculating equilibrium concentrations star, and then ice charts. That's the thing. That is the big important thing about this whole day. This whole day is about equilibrium, but the ice charts is the king/queen of the day. You need to know how to do an ice chart, and I will go through that and explain what that means and how to do them. In about 3 weeks, well, I mean, I always say that because I mean like in 3 meetings, if we're meeting in person from now, you would be able to do these in your sleep. Even if you say, no, I won't, I'll never be able to get this. Yes, you will. You'll do so many of them. You will do them while you're sleeping through osmosis. They are important. I always say, all you need in life to solve all problems are the following: duct tape, a little bit of beer, not too much because that causes more problems, and ice charts. Okay? Yeah, we could solve all problems with like North Korea if we just, send over, an ambassador with a handful of beer and duct tape and a calculation ready to go with an ice chart. Solve everything. Ice charts are king/queen, whichever one you want to be, maybe both, for the entire rest of the course. How to solve a problem using an ice chart. And they're actually not that hard. They're not. Trust me. Trust me. I think that's what Sitting Bull said to Custer just before the Battle of Little Bighorn. And it turned out pretty well for Custer. Oh, actually, wait, no, it didn't. Never mind. All right, where were we? So we're basically down here at the bottom. The next 2 problems I'm going to solve are going to be ice charts, and then there's this one quick review on something called Le Chatelier's principle, and we're done. All right, so actually what I'm doing here is I am, we just finished problem 6. We're actually going to skip problem 7. Because when I put it in, I realized it's actually it has a little bit of a tweak to it that makes it a little bit more difficult to start with than problem 8. Problem 8 is actually an easier problem to start you off using ice charts than problem 7. So let's do problem 8 before problem 7. So I wrote it down. Here's the problem. I took the liberty of putting some stuff down so I don't have to do it. Okay, look at the question. This is what's going to be the giveaway for an ice chart. Calculate the concentration of each species at equilibrium. So, what we're going to do, we're going to throw some of this hydrogen and some carbon dioxide into a container. I think it says 5 milliliters or 5 liters, and yes, it did. I wrote that down over there, 5-liter container. So you take these gases, you throw them in there, and you say, "Do what you do, gases," and they start reacting. When they start reacting, they're not in equilibrium. So some of you might be saying, oh, we have to do that Q thing because we're starting the reaction, they're not at equilibrium to do Q. No, we don't have to do Q. Why not? Because we only have the 2 reactants. We didn't throw a product in. Remember, the Q calculation is when we threw everything together all at once and said, figure it out. There's no figuring it out here. What's going to happen is we threw in the reactants, we didn't throw in any product, so the products are going to get made. Eventually, we'll go to equilibrium. When that happens, what's the concentration of everybody? Ooh, that's where you need the ice chart. The ice chart is going to be handy-dandy notebook figuring out concentrations at equilibrium. Okay, not at the beginning, at equilibrium. So, I need to figure out each concentration when this thing establishes equilibrium. Well, what we do know is in the problems, I wrote it down already, that we were given hydrogen and carbon dioxide, the 2 reactants. And we were told how much we were given. Each one we put in 0.8 mole in a 5-liter container. So we need to get the concentration. And we're going to use that. So let's go ahead and do that. We're going to need to get those concentrations. Equilibrium expression, it's a case C, so we need the concentrations. So 0.8 divided by 5 is 0.16. Okay, 0.16 is the molar concentration of hydrogen and carbon dioxide at the beginning. So we're taking these two, 0.16 of this, 0.16 molar concentration of this and this, and throwing them in. Well, actually, we're taking 0.8 of each one, throwing them in, and we're getting them to start to react in this 5-liter container. So initially, we start out with a concentration of hydrogen and carbon dioxide of 0.16. And I write that down below each one of the two. Ice chart. Why do you call it ice chart? Do you take ice and like rub it all over and make it nice and cool on a hot day? No. That does sound refreshing though. No. ICE stands for something. I. Initial. I initial. That's your initial concentration of everything in the reaction. The initial concentration of the hydrogen and carbon dioxide we calculated to come out to be 0.16. So we're throwing these two in the flask initially. All right, and that's the initial concentration. They haven't reacted yet. This is at the beginning, initially, meaning we don't have any of this yet because we haven't formed any yet because we just threw these two in. So initially, we have none of this. Put zeros there. Okay, that's what the I stands for. C. It's I-C-E, ice. Change. What's going to happen over time? What's the change going to be? Over time, these are going to react with each other. Spitting out some of this. So over time, we're going to lose this. The concentrations of these are going to go down. They're going to react with each other and make product. So we lose these. To show that, you put a negative. And you put an X. We don't know how much we're going to lose. We're not sure. We'll figure it out. But we don't know how much we're going to lose yet. Over here, what's going to happen over time? What's the change in these going to be? They're going to get made. We're going to get more of it. So this is positive. Positive. We increase these as the reaction keeps going. We don't know how much, so we put an X. All right, not so bad. I see. What about E? E means at equilibrium. Now, you might see these if you went and you want some tutorials online, which you can certainly do. I recommend that if you don't get what I'm doing. You know, I'm just not making it for you. You don't like my shirts. You know, you say I like my face, which I don't blame you for that. I mean, a lot of people don't. I don't like my face either. I look in the mirror and I go, oh my God. So if you go watch another tutorial, they might not do this. I do this. I put a line here. And because when I do that, it reminds me, and I tell my students, or it should remind you, that you're going to add these two lines together to get this line. This line is the combination of these two lines, and that's all it is. So at equilibrium, we should have how much hydrogen? It's going to be equal to 0.16. Take these two lines and just combine them. 0.16 minus X. That's why I put the line in. You don't have to. So here, the carbon dioxide will be 0.16 minus X. What's 0 plus X? X, right? What's 0 plus X? X. I now have my ice chart complete. Oh, we're down to the problem. No, we're not down to the problem. We have the ice chart complete. Now we're going to be able to solve the problem. We can't solve the problem until we get that ice chart complete. Okay, all right. Well, I forgot what we were. Oh, I remember. Figure out the concentrations of everybody at equilibrium. Here. I need to find out what those X's are so I can do that. How am I going to do that? Write an equilibrium expression. Let's write one. K is going to be equal to, remember what K is equal to. It's equal to the products And we include all of them, gas and gas and gas and gas. So this is a homogeneous equilibrium problem. They're gases, but we're not going to use pressures, right? Because remember, we use concentrations. We use concentrations. So Kc, how do we do Kc? Take our two products. I could go ahead and write down bracket H2O, bracket carbon dioxide, carbon monoxide, but I'm not going to do that because I know what those are at equilibrium. This is an equilibrium expression. Let's just put the x's in right here and save a little time. But I put H2O and carbon monoxide, okay, at equilibrium. And down in the bottom, at equilibrium, I take 0.16 minus x, 0.16 minus x. Now, you might say to yourself, hey, that looks familiar. I might have to do the FOIL method. Remember that from algebra? First, outside, inside, last? You could, but man, are you probably going to make a mistake. Even if you don't, if you do remember, you probably don't remember how to do that. So no, we're not going to do that. Let's go ahead and put the K value in first. I'll show you how we're going to do this, and it's not that bad. K value, 4.2. What's x times x? X squared. That's x squared. That happens a lot in these expressions. You'll get used to it. It's usually an x squared at the top. What about this? This is 0.16 minus x squared, right? Same thing multiplied by itself is squared. So 0.16 minus x squared. Now here's the tricky part about this one. You probably would not see this unless I pointed it out. So I'm going to point it out, and you will see a problem like this on your next test. So remember this. And when you see a problem that's very similar to this, because again, I'm going to put you, hopefully at this point you believe me after the first test, that I do put the same problems on the exam, so you'll see this one. And when you see it, remember this part. How do you get rid of a squared? How do you get rid of a squared? Take square root. Well, what you do to one side, you do to the other. Some of you might not have saw that. Some of you might have had to try to work through a FOIL method and then cross multiply, then take square root. Yeah, you can do that, but boy, you're probably going to make a mistake. That squared, this is squared. Square root both sides. If I square root this side, I square root this side. That makes that go away. And now I take square root here. Whoa! That made it a little easier. All right, let's take the square root of 4.2. We can do that right now. We can get the square root of 4.2. So second function square root, 4.2. 2.05. 2.05. 2.05. All right. How am I going to solve this? Algebra review, people. Algebra review. You've got to bring this up. You have to bring this up. So that's 2.05 multiplied by 0.16 minus x equals, some of you are getting very uncomfortable with this algebra. I understand. It's a review. Some of you are like, no big deal. But, it's a review, then go through this a couple of times. You gotta get the algebra. Okay, now what? You remember? Distribute. Distributive property. Distribute that through. All right, so let's see. I'm running out of room here. I will multiply 2.05 times 0.16. 2.05 times 0.16. I get 0.328. So 0.328 minus 2.05 times x is 2.05x equals x. Whew. All right. Oh, I'm getting the low battery on here. Oh, jeez. All right. Well, don't worry, we're almost done. So solving for x. Oh, look, like terms. I got an x and I got an x term. Let's add that to this side. Add that to this side. So add 2.05x to both sides. This goes away. 2.05x plus x. That's 1x. 1x plus 2.05x is 3.05x. So add 2.05x and this side goes away. Add it to this side, we get 3.05x. And that equals 0.328. Solve for x by dividing. So x is going to be equal to 0.328 divided by 3.05. Let's do that out, and let's get this problem kind of done. Ooh, don't worry. These will become second nature to you. They will. Trust me, they will. I know you're going, no, they won't. Oh, my God. They will. You will. So many of them will go through. You will get them. 0.328 divided by 3.05. 0.108. I'm going to round that to 0.108. All right, that's what x is equal to. Let's try to remember what the heck we were even trying to find. I don't remember anymore, right? What the heck were we trying to find like 15 minutes ago? Oh, we were trying to find the concentrations of each species, each one of these at equilibrium. When finally these things react and they form this stuff over here, and now we got these things finally settled and they're going back and forth equally, how much do we have of each one? We got that answer for these two right now. Water gas, carbon monoxide gas, concentration is 0.108 molar. X is equal to that. See, at equilibrium, these are equal to x, and that's what x is equal to, 0.108. 0.108. Boom. How would I do this? 0.16 minus x. So 0.16 minus 0.108. That looks like it's going to be 0.052. It should be 0.052 if I did the math in my head right, which I did. So if I take this and subtract it from this, I get 0.052. All right, so at equilibrium, let's see if the chemistry makes sense. It doesn't make sense at all. I know, I understand that some of you are having trouble with this. You need to go back through, watch this video again. You will get them. You will do so many of them. All right, now, does the chemistry make sense? K is 4.2, meaning that the products are favored. We should have more products at equilibrium than we do reactant. That's what that bigger than one means. More of this than these. Is that true? Yup. About twice as much. About twice as much more. We have larger numbers here than we have here. Boom. 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 That's what I'm talking about, people. Ice charts. Wicked important.